Okay, excellent. Hi, I'm Dan Thornburgh. I'm here to talk to you about LLVM-MOS, which is a C compiler for the 6502. Okay, thank you. Oh, wow. Okay, so yeah, I am its primary maintainer. I wrote the code generator and bunches of other little things. Also in my day job, I'm a professional LLVM compiler gremlin now. So that actually, there's a funny story about that because LLVM-MOS actually kind of was my on-road. I worked at a different part of Google and ended up just saying to a team that worked on LLVM, hey, I made this thing, can I work with you guys? And they were like, yes. And now I work on it full time, and amazingly, LLVM-MOS ended up overlapping with some of my actual day job things in a really weird way. So I'll talk about a lot of that. Okay, we can get started. So what is LLVM-MOS? I'll give one of these big word slide things, definitions. So it's a modern LLVM-based C and C++ toolchain for the 6502 and its platforms. So if there are words in here that you don't know, don't worry. I will annoyingly give background and go over these things. If you know everything about everything, then just tune out on your phone for a while. I will try to breeze through this in as reasonable a way for people that aren't familiar. And there may be things that have a little bit more depth than you'd expect. So I'll start with the 6502. If you haven't heard of the 6502, hi, welcome. It's 1975, now 50-year-old CPU, 8 bits behind tons and tons of consumer electronics from the 70s through to the 90s, well beloved, entered into popular culture. It was the Terminator ran on one famously, so did Bender. I guess they're still in use. And you know, that far into the future. There's also a few things that I'll specifically point out. It has a hardware stack, if you know what a stack is, but it's only 256 bytes, which is really, really tiny by modern standards. 8-bit arithmetic, also very small. It only has 3 registers. That's a very tiny number, and they're also 8 bits, which is very small. It also has a special region of memory, the first 256 bytes, called the 0 page. And that's very special, it's faster, there's special hardware instructions that deal with it, and all of that, again, is very strange. This will become significant later when we talk about how to actually generate code for one of these, but just keep this in the back of your head. I'll move on to talking about the 6502's platforms, specifically the ones that LLVM-MOS supports. It supports all of these, so it's a lot. Notably, I didn't write most of these. So like I kind of do the most LLVM compilery stuff out of anyone on the project, but the vast majority of these were just dropped off by somebody with full, basically everything that we support in terms of C and C++ for pretty much all of these. So there's a bunch of classic platforms, things you might not expect, like the Atari Lynx, tons of Commodores, new and old, and even sometimes people's hobby projects, like the Dodo is like a little tiny 6502-based game system. Similarly, David Given's CPM port to the 6502 is well supported. Just stuff that you wouldn't expect. RPC-8E is a Minecraft CPU mod that adds a 6502-based CPU to Minecraft. And Asi Kierke, wrote a backend for it, and we have one. So, you know, we also have a little simulator. So this also is not complete. Some of these targets have sub-targets. So particularly the NES, all of these boards are wildly different from each other in terms of capabilities, memory layouts, and so we support all of those too. For say the Atari 8-bit, we support standard executables like you might load through DOS, but also a ton of cartridges, all with their own configurations. Some of these boards have configuration flags that you can use to generate thousands of configurations for each of these. So the number of actual things that you can target with this has blown me away, and it's come together very quickly because we've made a lot of effort to make this thing as easy to retarget as possible, and LLVM has helped us a lot with that. So I'll then move on to talking about what it means to be a modern C and C++ toolchain. If you're not familiar with that word toolchain, it's one that kind of modern compiler engineers use to talk about the whole thing for getting C and C++ onto a device. So here's kind of a picture of that process. If you're not familiar with how modern programming kind of works, you have a language like C or C++ on the far left. And the job of a toolchain is to get it to a piece of ones and zeros that you can put on something that a device will be able to see, and then it'll make this physical object do something interesting that corresponds to the meaning of that C and C++ on the left. So typically you have a compiler which turns that C and C++ into an object, which is kind of an unfinished program. It's a program with little bits left stubbed out and left abstract. Things like printf. I say I need printf, but I don't say what it is or where it is. You combine that with libraries of other objects from your own code and libraries that are provided by a software development kit for whatever platform that you're developing for. The linker then connects the missing pieces needed by one object with those that are provided by another, producing, along with a linker script typically, the final binary. And linker scripts are configurations for this that specify the constraints on where things are placed, how things are laid out, and provide a lot of information about the specific requirements of a target and how the binary is to be generated. So that's the kind of 10,000-foot overview of what a toolchain is. When I say it's a modern C and C++ toolchain, I mean that you get modern C and C++ fixtures, the stuff that you would typically get in Clang and LLVM. So particularly, I like you get number embed for C from C23. This allows you to number include a binary into an array, and the preprocessor will turn it into a comma, like a list separated by comma of each byte of the array. So if you have a binary and you want to include it in your program as an array, you can just stick it in there or embed it. Very great. It also doesn't actually do that. It does it at a lower level, so it's not generating like a ton of text. And you get all the weird stuff that's been added to C. C++, you get even weirder stuff because C++. But even all the context for stuff, we actually make use of some of that. And we're pretty serious about standards compliance. Like what we have is and should be standards compliant. That being said, hold on, let me silence my phone. Okay, so language, pretty complete, pretty standards compliant. C++ standard library is just too big, and we don't really have the ability to port like libc++ in LLVM yet. So unfortunately, that means that our libraries are incomplete, but what we have is good and is like properly standards compliant. And we do a lot of testing along those lines. We're able to actually run a significant portion of LLVM's unit tests and integration tests, and they pass. We also run those in continuous integration every time we make a change to the compiler. We have a very modern like development and deployment setup on GitHub for making sure that that all stays working. We may also be the only people to be running an NES emulator in GitHub Actions, so I'm very happy about that. So we actually do like run end-to-end tests all the way down to like an NES. The one big exception is exceptions. No, we're never going to do exceptions. I'm sorry, C++ exceptions, the implementation of them on the runtime side is terrible. Nobody wants them, nobody needs them. We're just not. Unfortunately, I have to call it out as a ding because the C++ standard requires that they be present, even though like even major companies don't use them because of, yeah. Okay, and then the last part of this is LLVM itself. If you haven't heard of LLVM, it's a gigantic open source compiler infrastructure project. So this set of tools that I described, it's really one of three big projects that provide these tools, the other being GCC and Microsoft Visual Studio. And Clang tends to be the one that major corporations both contribute to and use, like Google, Meta, Apple, tons and tons of other companies, Nintendo, Sony, all develop and contribute this together, along with academics, people that are just hobbyists and want to see stuff happen. We all come together and hack on these compilers and libraries. So there's a C and C++ compiler, there's runtime libraries for things like addition and subtraction or multiplication on platforms that don't have those. A C standard library, C++ standard library, and also just other tools. That's kind of why it's called a tool chain. There's a bunch of tools that are involved in dealing with C and binaries. So there's a language server. You can hook this up to VS Code and get autocompletes. You can find all references. You can also have it automatically format your code in various styles. You can have it lint semantic issues or undefined behavior and automatically fix them. And LLVM-MOS provides ports for all of these. Everything on this slide except for the libc and libc++, because no. I'd like to eventually have libc++ compiled, but that's like a very big long-term project. So that's the thing. Congrats, you now know what LLVM-MOS is. What can you do with it? It used to be, it is not anymore. Okay, I'm not going to be able to talk about this. So LLVM used to stand for low-level virtual machine. And it used to be that you were going to compile to a virtual machine and then JIT it. And then they decided, no, we're not going to do that. It's just going to be a compiler. But the name was still low-level virtual machine. So we're just going to say, no, it's not. It never was. It's LLVM. It's a meaningless series of letters. It's fine. Yeah. Okay, so that's LLVM. This is the part where I get to show off weird, cool demos, things that people have done with this. I had nothing to do with any of these for the most part, except for this one. This was the first demo that I actually showed off at Euro LLVM when I presented this to the LLVM people. And this is 500 lines of pretty high-level Rust running on an Atari 800. So Rust, the very modern programming language, uses LLVM intermediate representation as its kind of backend, and then just defers to LLVM to compile down to machine code. And in 500 lines of Rust, someone was able to make a little demo with this is the Rust mascot crab Ferris, dancing around with a little greet scroller. And this is very straightforward, very high level. That's one of the things that LLVM-MOS lets you do is write surprisingly high level code and have it come down to something sort of reasonably okay on these platforms, which puts it decidedly in kind of the newer generation of C and C++ compilers for this. We're not the only one that produce reasonably good code at this point. There's actually a surprising number. But it's much divorced from the older generation of these that you would expect to produce code that is like between 30 to 100 times slower than what LLVM-MOS and its cadre are capable of producing. But that's actually old news. I'll move on to something a little bit more modern. The NESDEV Compo 2023 had this as its third place entry. And this is 6,500 lines of C++. Really, really high level C++, using some of the newer libraries that we have for structive array and other things. It's a game where you have two players and can, in either single player mode or double player mode, control a character while someone else is playing Tetris, and then Tetris fills in the maze, which makes it inaccessible to access to parts of the maze. Really fun little concept. And it's not a super intensive NES game, but it's kind of like it's real time. There's a lot of effects. There's a lot of sound and music and stuff that has to happen on tight tolerances. And the compiler is capable there's almost no inline assembly except for the sound engine, which is in assembly because it was brought in from another project as a library, which you can do. On the other end, somebody actually ported Linux to the Commodore 64. So this is a port of an existing RISC-V emulator, which was specifically designed to have just enough functionality to run the Linux kernel. Somebody then took that, and it was in C++, so he just compiled it with LLVM-MOS, and it didn't fit, of course, so he used a 2 megabyte RAM expansion unit and rewrote the emulator to do virtual memory with the RAM expansion unit. And then there's a YouTube video of this. In 48 hours, he got the Linux kernel to boot on a Commodore 64. I didn't watch the whole 48 hours, but the Twitch live stream was very exciting that couple days. I was watching with bated breath to get to who running here, and he actually got to a user land with BusyBox, which is incredible. This is my favorite project that anyone has done with LLVM-MOS. There is a Linux kernel module on GitHub called ublurandom, which is a replacement for urandom. urandom produces boring binary numbers. This produces random catgirl noises, as you might see on various Discord forums. Someone, of course, took this pure C library, took out the Linux kernel parts, ported it to the Nintendo Entertainment System with a new GUI, and you can now get the NES to generate catgirl noises for you. I actually put this on a flashcard and have done demos here at Relics and other meetups and stuff, and it's a good time. It animates yeah, okay. Anyway, there's other stuff that isn't quite so visual to put on slides. Somebody ported Zig similarly. 2023 Christmas, this guy, whose name I unfortunately cannot pronounce, I think he works on the V8 compiler engine, but he decided I'm going to do the entirety of Advent of Code 2023 this Christmas using a custom IDE on my Commodore 64 that sends code to a remote computer running LLVM-MOS and then sends the binary back, giving me an actual REPL for C++ on a physical Commodore 64. He did this before we had finished our studio, and so just in stride wrote the rest of our studio in his local project. and finished every single bit of Advent of code that year on a Commodore 64, which is incredible. David Givens also did two really, really cool projects, a CP/M port using the original assembly sources annotated line by line to the 6502, and was able to use the fact that our compiler is, has relocatable objects and take those relocatable objects and build a relocatable object format for CP/M so that it could deal with the differing memory maps between all of the 6502 systems that one might want to port CP/M to. So he was able to get a version of CP/M that has the Z80 property where you can compile a binary to it once and it'll run on any 6502 computer that he's ported it to. And he's got like now, I think 24 ports, which is really cool. He also was able to port it to this, write an SDK for these weird Tony 1.8-inch game consoles that are popping up on Alibaba, which he reverse engineered and discovered were weird 6502s and was able to make an SDK for them. So lots and lots of stuff. This is not even exhaustive, of course. All that being said, this is something that I've heard over and over and over again. You might have been coming in here with this in mind. You can't write a good compiler for the 6502. I can't count the number of times that I've heard that. Or variants of this. That's not actually what I had up on here, although it probably should be. I don't think that's actually true anymore. Like, if it was just our compiler and it required a truly Herculean effort, it would be one thing. But enough people have tried enough approaches and gotten good results out of C and C++ compilers for the 6502 that I think this is pretty bunk. I think if you want a true statement along these lines, you have to move to something like this, that it's a difficult compiler target. There's a standard set of techniques that are used to move from high-level code down to assembly. And those techniques, applied naively, do not work well for the 6502. It wasn't designed with those techniques in mind, like many modern chips are. But compiler people are tricky. We do weird stuff all the time. And if you try to do kind of normal degrees of weird stuff to this problem, it's surprisingly amenable. And I'll cover quite a few of the things, the weird tricks that we used to actually get this to work coming up later in this talk. So, actually coming up now in this talk, I'll begin by talking specifically about how LLVM works. This is not going to allow you to go and start hacking on LLVM. I'm sorry, this is only a 45-minute talk and LLVM is, but it should give you an idea of what the things are called, where they're placed, etc. So I'll start with Clang. Say you have C++ and you want to compile it to something. Kind of this is the compiler, like the actual part that cares about C and C++ is pretty well represented here. You start by parsing it, which is saying, what does it say? What are all of the words? And this is where you'd get errors like you left out a semicolon. Your words are wrong. Once you've understood the words, you build a data structure called an abstract syntax tree, syntax being words and their relationships to each other, and then you semantically analyze it. You say, what do these words say? What do they mean? And this is where you get errors like, this type has a 0 length, and that's not acceptable here. Once you've done that, you do code gen. You produce an intermediate representation, which is kind of like a very, very high-level assembly language that has the stupidest possible implementation of the meaning of those words. And then you're done. That's actually all Clang, its LLVM C and C++ compiler does. And that's kind of intentional. The goal was to keep the C and C++ part of this as simple as possible. And even having done so, writing a C++ compiler is so nasty and hairy that Clang is huge, even though it doesn't do a lick of optimization. It is incredibly dumb and short-sighted, the stuff that it spits out. But the very next thing that happens is LLVM picks up. And the very first thing it does with this stupid, stupid IR is optimize the crap out of it. It runs hundreds and hundreds of passes designed to massage away all of the stupid. And it does so. What comes out of that is surprisingly good mid-level intermediate representation that has things like tons and tons of constants folded away. Things have been inlined into their locations. You know, this is kind of what one thinks of when one thinks of an optimizing compiler. All of that happens completely before it gets to us. Most of this stuff is completely target independent. It doesn't matter what system you're doing this on. And because of this, I have no idea how any of this works. Not exactly. I have a day job where I have to care, but you know. The next thing that happens is it gets translated into a representation called MIR. And this is also a very stupid step. Each MIR instruction corresponds to exactly one LLVM-IR instruction at this point. This is just pro forma. It doesn't do anything. But MIR is a data structure that is modeled after real machine instructions. And unlike LLVM-IR, which is intended to be this abstract thing that encompasses meaning, this is supposed to be about actual line-by-line assembly. So we make a fake version of the assembly, as if we actually could execute LLVM-IR. And then the task that we have as an LLVM backend is to slowly massage that into real machine instructions. That is kind of where we come in. So the very first thing we do is we legalize it. We say, this is a 16-bit add. I can't do a 16-bit add on a 6502. And now at this point, it doesn't say anything about where those operands are, like what their shape is. We don't know. All we know is we can only do chained 8-bit adds. So we rewrite it. And LLVM actually provides a lot of help for this. You can just tell it, rewrite 8-bit adds to 16-bit adds to 8-bit adds, and it'll do it for you. And we get it then to a shape where if you squint at it, you're like, oh, these are all things I could plausibly do on a 6502. Now it's closer to 6502 assembly. And I haven't made any decisions that weren't obvious. But then these still really aren't 6502 instructions. But we might look at this and say, oh, here's a load, and then an add with 1, and then a store to the same location that we loaded from. And if you know anything about 6502, you might be, that looks like an increment instruction. So maybe I could just take that whole thing out and replace it with an increment instruction. That's how instruction selection works. You actually just have a big pile of C++ that looks for patterns and then rewrites them, again, to completely abstract 6502 instructions. And still, if you have like a compare, you can say, oh, I can compare about A against A, X, or Y. I don't really know which it's going to be, but I'll just say it'll be a compare. I'll figure that out later. You only make decisions in one of these passes that are obvious. And that's kind of the idea. You deal with one obvious concern at the point where it is obvious and try not to do anything that isn't obvious. And you can get surprisingly far with this. Once you have instructions, it becomes much easier to decide where to put everything globally. LLVM is a register allocator, which can say, oh, if I can minimize copies, if I put X here, A here. Similarly, once I know a more realistic instruction sequence and where things got put, I'll know how many local variables I need to handle spills from this point where I couldn't find registers for things. And I can lay that out into a frame for each function. And then I have a better picture of all of the actual instructions in one of these blocks, a block being a region of code that has a single entry and a single exit and always executes together. You could say, oh, I can kind of rearrange the positioning of these to minimize the number of branches that I have because I know how long they are. Branches have only a certain distance that they can hop. And so you can do that. And now you have pretty much final assembly. So all that's left to do is spit it out into assembly. And at that point, the backend is pretty much done. I actually don't know how well this works very well. I didn't write it. LLVM-MOS actually was a project that had an assembler in it by the time that I came onto the project. I wrote most of the stuff in here and have only begrudgingly needed to deal with this as maintainer, as bits that have broken and I've had to rewrite those parts. So yeah, that actually is kind of the story. What I have not talked about is what parts of this are weird for the 6502, the stuff that I mentioned earlier, the stuff that this usual pipeline does not really tolerate as well as one might think. So I'll start with the big raison d'etre people give for why you can't write good 6502 code in a compiler, which is the stack. That's kind of the standard reason that CC65 code is terrible, because it spends all of its time manipulating a software stack. And there's a good reason for that. The 6502 does have a hardware stack pointer, and you can kind of use it for stuff. You can even do fast offsets from it, but it's too small. Like if you have, say, 50 deep call stacks, which is not that unreasonable, like you have very few bytes when you include the return out value and a couple locations. It's not enough for all of the local values in a typical function in something like C or C++. So you can maintain a software stack pointer, but it's really slow. Like you can see the cycle counts for entering or exiting a function, accessing a variable. And traditionally, our competition, assembly language programmers, they don't do this at all. They just say, okay, I'm going to look at the program. I don't need a stack. I'm just going to put this here, this here, this here. Variables are just put in memory. And the reason they can do that is because they have a sense of their program as a whole. They're not looking at a function at a time. They're looking at this whole thing. And they're like, well, I mean, I specially designed this region over here to call itself. F can call H can call F, so I can't have a single location for either of these. I'm going to need to build like dynamically a region, but I designed it that way. That's sensible. But all of this stuff, you know, these can't call themselves. There's only ever going to be one instance of one of these active at a time. So I can just take those and I can stick it in memory. And then I'll have a dynamic stack just for this variable region here, the things that can call themselves recursively. And so we do that. We actually have the ability, using link time optimization in LLVM, to get a picture of the entire program all at once. And so we walk the graph, find out which regions are cyclic, and then, you know, everything else, mark that it can't recurse and assign it to static stack or to the 0 page. More than that, you can look at some of these and you can say, oh, C can't call G and G can't call C. That means they're independent. So C and G cannot be being called at the same time. So I can stick them on top of each other. This is something that assembly language programmers tend not to do because of how brittle it is. If you insert a call, you'd have to rejigger where you put everything. But a compiler can just do that. So we've noticed that we can tend to use slightly less stack than most assembly language programmers are willing to use. Or sorry, not stack, the virtual stack. And this actually works surprisingly well. This is all completely automatic. It just sort of falls out from the stuff that we do. And we also found that doing this, most programs that we've seen tend not to use the dynamic soft stack at all. It's available as an option, but you don't actually have to use it. So that's the stack, honestly. That mostly takes care of that problem. The other big problem is the register allocator. So LLVM was not designed to work with a chip with 3 registers. There's just no real way around that, I mean, except for the way around it that we found. So particularly, you have 3 registers, and they're not the same. The 2 things that it assumes are you have a lot of registers and they're all the same. Not all the same, but like they're in big classes that you can copy between them. You can't copy between X and Y except through A, so it's just nasty, the constraint that it needs to solve. It throws its collection of tricks at it, and then it fails. It says, I ran out of registers, which is another way of saying, I couldn't fit it in there. I'm sorry. So what we did is expanded out the scope of what it had to play with. And this, again, is kind of similar to what assembly programmers actually do. The 0 page is kind of like registers. Not exactly, but you could squint at them and be like, oh, well, I could reserve a region and just, you know, I'm going to pass things in and out of functions anyway. What if I just always do it with temp1 and temp2? I've seen people even write code that way. Okay. Okay, I've seen people write code that way. And if you do that, our register allocator is pretty pleased with that. You can see that we have RC0, 1, 2, 3. These are like bytes. And then they are joined into pairs, so you can do things like loads from indirect addresses using these registers. And with our software development kit, you can use the linker scripts, which remember are the scripts that kind of tell the layouts and memory regions available to specific targets. You can use that to place these bytes and byte pairs anywhere that you want in the memory map. So this has given us a great deal of flexibility. 6502 memory maps are weird and all over the place, but anywhere that you can stick 32 bytes, don't even need to be contiguous, will allow you to port LLVM-MOS in its full glory to it. And we haven't really found this being trouble on most platforms, especially since if you're writing your own assembly code, you can make use of these same set of registers under the same calling convention. And that's kind of the recommended way to write assembly if it's going to interact with C. Next thing to talk about is not actually inside the compiler at all. Those are kind of the 2 big things that the compiler needed to deal with, and they are pretty handily solved by those 2 techniques. The biggest other thing is the linker and the linker scripts, because output formats. If you look at how many different file formats these 6502 platforms that we support are supporting, it's almost 1 per. You have executable file formats for all of these machines that have operating systems, and for the ones that don't have operating systems, you have cartridge ROM formats. And the latter are determined by hardware. One platform, the PC Engine, actually has a CD port that we support. So one of the targets requires CD ISO images to be generated. And this is kind of concerning for us because, well, for our own purposes, we need libraries and output files and all of those things to connect things within this toolchain. So Embedded software toolchains typically use ELF for this purpose, just because it's kind of the best supported. And then you generate binaries from ELF somehow. But to do so requires tons of information from the linking process, tons of information from the binary. And so a usual way to do that is require people to write C++ that copies things from ELF over to whatever the format is. And I considered this an existential risk for the project. Like, people would not contribute new backends if doing this required you to write custom C++ parsing ELF. It just would not happen. So we needed a way to do this that didn't require that. And so we wrote one. The linker script language to that, we added an output file builder sublanguage. So you can say output format, and then you can, oh, by the way, this is a snippet from the actual NES header. The format that is used for NES ROMs is called INES2, and it has a bunch of bytes that have information about what the mapper IC is, content, how big the ROM is, the ROM itself. And you can output those bytes using expressions that are known to the linker because they're just available in the program, like what the mapper is. That's a symbol, the submapper. And then you can build that and pack that into a byte as is expected by this file format. You can also output the contents of the image that the linker has been collecting. And you can do those in interleaved fashion in line. You can also include other files into this. And the sublanguage we've found has allowed us to more or less generate the vast majority of the file formats that we actually need to in a way that doesn't require writing any custom C++ and with just the constructs that are on screen. It is remarkably general for how small it is. And I'll give probably the worst example of this in our SDK. If you've ever written NES code, the MMC1 is a particularly nasty piece of work. This is the most common mapper ASIC used on the NES. So this is a little chip that goes onto an NES cartridge, and the purpose of it is to control the memory layout as visible by the CPU. There wasn't a lot of memory that was actually accessible by that hardware architecture. So typically larger games, and games could be up to 512K, they would bank it in and out by using the controls on this chip. And this thing was weird. It did everything that it could to minimize the pin count and cost. And so when it turns on, its state is completely undefined. They didn't add a reset. So it will go out of metastability to something. And what that means is the bank is question mark. Now, the CPU, when it comes up, it'll go looking for a reset vector. And it'll go looking at, from its point of view, 0xFFFC. Please don't, harm me after this if I was wrong about that. But which bank is that in? We don't know. There's no way to know. So production NES games, you actually can find this. The solution to this got called the Barbie reset because there was a snippet of code that people in the homebrew community particularly liked that was used in the Barbie game for the NES. I don't know why Barbie, but yeah, the solution to this is the Barbie reset. So at the end of every bank, you need to have a snippet of code compiled for the end of that bank that sets up the bank state. And then you need to jump to the, fall through to the same code at the same offset. So you'd have instruction, and then at the end of that instruction, the bank state would change, and you need to fall through to the next instruction, which will be in a completely different bank, the fixed bank. And then you need to continue on with that. So you need these 12 bytes in an exact layout in every bank of this, and you need that all to come through the program image. Make that worse, the number of banks should be configurable, because you could have varying amounts of ROM with this. Any power of 2 should be supportable in terms of the number of banks. So we can actually do that with our linker script language. We can express all of it. You can have the program ROM sized be accessed in the linker script's description for each of these banks and say, hey, did they configure that the program's ROM size should be at least 64K? Well, if not, we shouldn't have a bank here. Otherwise, we should. And the size of it should be subtracted, should have 12 subtracted from it because we need room for that stub that's going to go at the end. And we can compile that stub of length 12 against an arbitrary bank. I think in this case, I chose the first bank. And then in our output format, we can output the contents of each ROM, the full there for 0 and 1. And then we can do this expression. So I'll actually unpack this. Full reset, that's to say, put the contents of reset here, and I'm going to trim it. I'm going to trim it starting from byte 0, that is to say, from the beginning. And then the length of that trim will be this expression, which is, oh, did we have ROMs at bank 0 present? then take the whole reset vector for that back. Otherwise, don't do anything. So we actually have things like conditionals and ternaries in this language, and you can use this to build an image that actually works for any configuration of the MMC1 mapper. And this is all crap that you would have to do yourself. It all really is core to this mapper, this chip. There's not really a whole lot of ways to use this thing, but every single NES project before LLVM-MOS came along would have to do this themselves. And this is kind of, to me, the crowning jewel of our setup, is that we were able to use this advanced tooling, provide an SDK that was configurable enough and flexible enough to hit tons and tons of different configurations of these common pieces of hardware, so that you didn't have to care about it. Like, the tooling would just take care of it for you. And not in a, we only handle the 3 most common configurations way, like in an actual configurable, like combinatorically complete way. And that actually worked well for us. Like, that's kind of the sauce that let us support all of those platforms that I showed earlier. People were able to use this to do nonsense. So that's that. The other piece is the actual libraries for this thing. So porting C and C++ to something is hard. There is a lot in the C runtime. If you've never written a C runtime, there's a lot of stuff that has to happen before main and stuff that has to happen after. And we didn't want people to have to deal with that. And in LLVM-MOS, they don't. So the targets will actually depend on each other in a way that is hierarchical. So we have a common target. And that has everything that any platform that is supporting C needs. But it doesn't say anything about how that stuff is used. It provides libraries for dependent targets, and it leaves hooks undefined for things that you know you'll need, but you don't know how they'll be spelled. Then we have an NES target that depends on it, and it fills out all of the NES-specific parts of that, all the questions that you could answer just by virtue of being on an NES. But then it leaves its own set of hooks undefined, and it provides its own libraries for more specific targets. And MMC1, which I just showed, depends on that and fills in the gaps. Notably, these incomplete targets, you can develop against yourself. And that's kind of how we've tricked people into porting this thing. In your project, you can compile against NES if we don't have a target for your mapper. And then you, in your linker script, can use the libraries and fill in the hooks to get it working on whatever weird piece of NES hardware that you have. And then, when we see that you're doing this and you start asking questions about it, we'll say, hey, you know, with just a little bit of work, this would be really slick to upstream into our SDK. And then we'll trick you into doing work for us and allowing, of course, everyone else to benefit from the work that you were doing anyway on your own project. And we've used this to build out a huge library of really excellent configurations and libraries for these. We also ported a lot of stuff from CC65. We tried to maintain compatibility with CC65 in terms of the semantics of file operations, stuff like that. That did give us a leg up on some of these platforms, but a lot of it also is bespoke. So one other weird thing we did. Here's an actual downside of LLVM-MOS. It's UTF-8 only. There is upstream work by IBM to add different execution character sets to LLVM, but it's very unpopular because most people don't know this. The character set affects the preprocessor, it affects the C optimizer, it affects the ABI. It's actually kind of nasty to switch out character sets for a system where you're going to have libraries. You know, imagine that you say number if A double equals 65. What's that going to do? Like, say you have code that you grabbed in from somewhere else and it has code like that in it. It needs to know what the actual numeric value of every C character are. And so it's not a mild thing to switch out from ASCII on real code. So ours is just ASCII, which means the standard requires we do some runtime translation from UTF-8 to whatever the target character set is. And we do that, and that has a cost. But that always kind of sucked, and we wanted to find a way around that. So we did. C++20 lets you have character set literals, and then it lets you run const eval functions at compile time from a header on those literals and generate new static variables with new contents. So we have a little library that runs over them and does character set conversions at compile time in C++ without macros. And so you can say Unicode string hello and then say _u for unshifted PETSCII on a C64, and you'll get an unshifted PETSCII string out of it that's zero terminated. Moreover, symbols for legacy computing was a recent Unicode effort that we took advantage of. So we have now official mappings, and you can put any character from any of the targets that we support this on into your source, including like PETSCII characters, and they will come out as the correct characters in your program, which is very cool to actually see. You need a font with those characters in it, but there are some like whole Unicode fonts. And this lets you directly output things to hardware. We support both the ROM versions for video ROM and the actual like transfer ASCII variants. And you can also use Binary Studio to turn off the translation. And this actually just kind of works. It's neat, C++ only, but it's one of the cooler things we've done. We also, like I mentioned, I'm a daytime compiler gremlin. So I have done some stuff upstream that I can talk about. One of the things that linker scripts require you to do is to put stuff in banks. If you have banks, you have to manually put files in banks. This is terrible. This is the kind of thing computers are meant to free us from. So Upstream, and this is now in LLD, we added an extension to the linker script language that lets you assign stuff to classes and say, here are the places the classes can go. Please assign them as you see fit. Spill from one to the other when you run out of room. This is kind of how everyone would assume that it worked anyway. Now it works that way. We can use this in LLVM-MOS, although we're not yet. I also added a little ylive thing from another linker to when you're garbage collecting code and data and stuff doesn't get garbage collected correctly, to give you a little trace and tell you why was this thing referenced? What referenced that? What referenced the thing that it referenced it, etc. Here's a little example on printf. Printf came from main came from start. You get it. Nice little feature I spent time on. The biggest thing I'm working on now is modular printf. This is a way to replace printf with, okay, the people that know. Printf is enormous. Wouldn't it be nice if you had the compiler scan a particular use of printf and rewrite it to a minimal printf that doesn't have anything brought in by default and then emit symbol references to bring in to the link the parts of the implementation that were needed. This is something that we're working in upstreaming, and this will be part of LLVM-libc, but will also be something that we could add to any other libc, such as newlib or picolibc or the other ones. It's actually just an attribute that goes on printf-like functions. We're starting with float, but we want to extend out the language to have tons and tons of specifiers and give you a really fine grain of printf-iness. And I'll briefly talk about future work, directions. I have been working on a new register allocator for LLVM-MOS for more than a year now. It sucks and is bad. LLVM is just really still not intended to do this. We ended up with really weird stuff to get the register allocator to behave plausibly. Really everything from instruction selection to register allocation we should be doing ourselves, but we're not. It's something that I'm still actively working on. I have better ideas now of how to do it than I did before, but it's just a gargantuan task to rewrite all of that stuff. But that's kind of the biggest thing that is holding us back from really meeting the other next generation compilers, particularly Oscar 64 has better code gen than us because of this. And if we can rewrite that part of LLVM, then we'll be back on par with all of the other advantages we get, like I mentioned, from being part of LLVM. We'd also like automatic banking. In particular, banking, here's kind of just, I'm running out of time. So a broad overview of a mathematical approach to handling banking. You associate code or data with a number. You say to the compiler, making the state of the system correct to access this number might imply that you can access this other number for free or prevent you from accessing this number if you were previously able to. And you could provide constraints that would allow you to model essentially any bank setup that way. And then the compiler with that model would be able to correctly insert bank switching calls that you could fill out yourself, or fixed bank routines to do loads and stores if that didn't work. And then you wouldn't have to deal with that anymore. And if you couple that with the automatic placement stuff that I mentioned earlier, particularly profile-guided automatic placement, which is something that I'm working on upstream, then this would give you a complete automatic solution to packing your code in banks where things that are used together would be allocated together by default, which would be really, really nice. And last but not least, John Bird, not me, is working on LLDB support. The idea is that you have a remote access protocol provided by GDB, a simple serial protocol, and emulators would speak this protocol and export the ability to do like reads and writes. Then LLVM-MOS emits dwarf debug data into the ELF file that comes out of it. And LLDB uses this to find variables, do reads, do writes, call functions, and interpret the results. This is kind of early days, but he's gotten surprisingly far in this. The main obstacle now is that the debug data coming out, we didn't really look at. So it's pretty bad. We need to go through and make sure that it's preserved through each of these pipeline passes. The other thing, please, someone write us an Apple II target. It's the weirdest omission. It's just that nobody really knew like what shape it should take. I'm not an expert on the Apple II. No one present was. Just no one has really, please, anyone here, you, if you know the Apple II well, help, write an Apple II target. Yeah, that's the whole thing. We have a wiki with tons and tons of information about all of the details that I left out, obviously. You can also look at the projects, both the SDK and the actual compiler fork on GitHub. We have an active Discord. I'll be posting the slides as a pin on the wiki, and that will have all of these blue links were actual links to all of the things that I referenced in this. Okay, I have probably a couple minutes for questions if people have them.
The mic, so if I can go to the
Yeah. We do.
Okay, well then that'll take care of a lot of your allocation.
No. Okay, yeah.
So I feel like what you're talking about with the registry allocation and automatic banking kind of gets to the heart of this question, which is like, how well can you describe some of the bizarre constraints to the earlier stages of the LLVM pipeline so that like if, for example, you have to convert a 16-bit ad into two 8-bit ads, is that something that the earlier stages can kind of know about so they generate better code that's not like full of them? Or
if I understand the thrust of your question, this is something that was counterintuitive when writing one of these. That imagine breaking down, like I mentioned in the legalizer, a 16-bit ad. Say you do an 8-bit load, 0 extended into 16 bits, or sign extended, then manipulate it, and then put it back into an 8-bit address. Imagine then expanding that out into a series of chained 8-bit operations. The compiler will see that the upper 16-bit of that whole chain is dead. Or maybe just that the very end of that chain is dead. And then it deletes the end of the chain, and then notices that the next end is dead. And then without any special logic being present for it, just with normal dead code elimination and expansion, tons and tons of code gets deleted. We found that accounts for essentially 85-ish% of making sure 8-bit things stay 8-bit, regardless of what the C standard says. There was a little bit of extra stuff that we had to do with regards to loops. That kind of straight line reasoning can't see through loops. And we found that that's essentially the only construct that it can't see, because they're cyclic, not acyclic. Everything ends up being used by something. But LLVM also has all of its loop stuff in the target specific part of the pipeline for that reason. And so there were hooks that we could extend to teach it poorly that 8-bit operations were infinitely more preferred when it was choosing loop index variables over 16-bit operations. Together, that mostly takes care of it, I think.
That's kind of the other like half the questions with the virtual registers. Can you tell it like A and X, Y are very fast but weird, so like it does good register selection for like when it has to use the virtual ones versus it can actually use the hardware ones?
No, but that's kind of why I'm working on a new one. To get that fine grain of detail for, I'm thinking that we'll actually need to do something like, you can do super optimization with 3 registers just by doing dynamic programming with, there are 3 slots. So you end up with n cubed to do a scan and decide what should be an A, X, and Y simultaneously. And that's not actually that bad in practice. So that was on a recommendation from a compiler guru on V8 that I talked to at work. So yeah, I think we need more sophisticated techniques to get the best results. Right now, our stuff has way too many copies from imaginary registers to others just because, yeah, the register allocator thinks they're free, and they're not. But that kind of chaff, it's not great, it's not bad. It just kind of muddies the water and sometimes produces very big code when there isn't the need for it.
Hi, do you do all the scalar types, 32 and 64-bit int and float and double? I know it'd probably be all terrible, but do you provide all those data types?
Yes, we provide all of them. We provide 128-bit ints too, if you want them. We also provide 56-bit ints and 23-bit ints. And so LLVM actually has a bit int type, and our code is recursive. So when we break things down to 8-bit operations, we actually do it for truly arbitrary bit widths. Because you can just round up to the next 8, and then you can break it down in bytes from 8. So we actually wrote it that way. So you can support arbitrary. We don't allow you to multiply arbitrary sized integers, but you can do adds and subtracts and some operations on them. The compiler might balk at you if you try to get too fancy, but we found real use for 24-bit ints, by the way. Like those are useful in certain contexts.
Do 8-bit near pointers, 16-bit bar pointers?
We do have 0-page pointers. They don't work. So some of our extensions don't work. We have it, they're buggy. Sometimes they work, sometimes they don't, but no one is using them. So, the work to go in and fix them just kind of hasn't happened. They're kind of an oddity in the first place. The compiler uses them internally. Those uses work. But we tried to export it to the user, found that people were hammering them. They didn't work. So, yeah.
As someone who's interested in implementing a similar project for, say, the Data General Nova, which is a spiritually similar architecture, I would say. It's got a lot in common conceptually, even if it is 16-bit. How do you even get started on something like this? What resources would you recommend for somebody who was trying to follow the same path as
int
you?
main return 0.
Int main.
No, seriously. I tried to do what you just described with something like LLVM. Like, I'd recommend using LLVM or looking into it, honestly. It saved us a ton of time. Especially if the Data General Nova is any bit more normal or bigger than a 65. Okay, well.
It's got 16 bits, but the instruction set is crap.
Okay, that's easier. Crap instructions, easy. Crap data, terrible. And that's what made the 6502 so hard. Like, everything that I mentioned was how bad the data structures were. Pointers. If you have good pointers, you're fine. If you don't have good pointers, you're sunk. So I'd recommend, if you want to get started with LLVM, anyone who wants to, just trying to get things set up to pass through all of the pipelines in a new backend, and int main return 0. I learned more doing that than I had in every bit of introductory material that I had. Because LLVM and many projects like it are not documented. Really. There is documentation, but they are not documented. The expectation is that you learn by dealing with them. And the best way to deal with them is to deal with them, but not in a way where you're trying to do anything more than the absolute bare minimum. You pick a very tiny, stupidly tiny goal, and then try to achieve that, and that will orient you for the next goal. And that's how LLVM-MOS actually developed. Like, I had learned enough by the time I finished int main return 0 to build slightly more. And things ballooned out remarkably quickly from there. But it is time consuming. There's no real way around that. So I think we have 45 seconds left. Does anyone have a question that could slot into 40 seconds?
65-bit 16.
We have assembly support for it. Writing a compiler for it is comparable to a whole other project the same size. So we do have CEO2 and like lots and lots of other variants. We actually, ASCII-Kerka added all of the weird memcopy intrinsics for the PC engine because, they're an absolute, mad person, and they really, really like the PC engine, which was very cool. But I don't think we have any other targets that have that degree of support. It really is just a matter of someone coming in and spending all of the time needed to figure out all of the stuff. And compiler-y people are a rare breed, and there's not many of us, especially in this space. So, okay, cool. Thank you very much.